So last time, just to remind you, I wrote down this type signature, and we had, just by kind of following the types, playing this kind of type jigsaw puzzle game, we had come up with an implementation that Haskell was okay with, at least in terms of the types, but it didn't look useful. And so, well, that was like, we take this F, we need to return an A, so we could call F on something to give us an A, but we need an A to give it. And it looks like we don't have an A, but we could call mystery again, like this. And this, in fact, this looks totally useless. It turns out it actually can be quite useful. We'll do some examples and see why. This is, in fact, called fix in the standard library. Okay, so the fact that it's in the standard library tells you, okay, there's something more going on here. It's not just like this weird, useless. It looks just like it's going to be infinite recursion. Like, how could anything ever actually come out of this? If it just, all mystery F does is call F on itself. It's like it's not going to make any progress. Okay, so, and surely, certainly, so let's see, if I, okay, so certainly if I do like mystery, let's say I pick the type, so when I call this, I can pick the type A to be whatever I want, right? I can pick the type A to be int, right? So then I have to give it a function from int to int. So let's say like +1, right? That's a function from int to int. And then it promises to give me back an int. What int do you think it's going to give me? I mean, the answer is it's not, because it's just going to sit there, it's in an infinite loop, right? I can kill it. Stack overflow, right? I mean, so like that is not actually useful, because it's just calling +1 on itself over and over again, right? So mystery +1 or fix +1, I could also say fix. It's the same thing. Oh, I gotta like input it like this. Where do I input it from? Data.function, okay. Do y'all know about Google? We talked about this? No? Yeah, okay. Well, google.haskell.org. Right, it's like Google but with an H for Haskell. It's like, probably like copyright violation or something. This is a nice tool. So you can search for things by name. So like, I wanted to know, I was like, I know there's this fix function. I don't remember where it is. And so I just searched for it and found it here. You click on this and take me to the documentation. Just need to type, right? It's in the data.function module, whatever. But the cooler thing that you can do is you can actually search by type. So let's say you're like, all right, what I really want is a function that will like take a number, like I wanna take a number and a value and make a list with like, but that value repeated a bunch of times. So like, if I say, 10x, it's gonna make, a list with 10 x's, right? Is there a standard function that does that, or would I have to write it myself? Well, I don't know what it's gonna be called, right? I mean, you could try like guessing names and searching for them, but that may not hide it. But you can search for the type. So you can say, well, I know that function is gonna have type, it's gonna take an int and like something of type A and give me back a list of A's. Right? Oh, replicate, there it is. Indeed, that's what we want, right? And it doesn't just search for the exact type, like it'll find other things that kind of match it. It's like, it has like similarity score. So even if you didn't get the type exactly right. So actually I wonder if I say like A to int, the list of A, will it still find it? Yeah, it still found it, right? It's like, oh, this is kind of similar, it's just that arguments are in other order, so you don't even have to get the type exactly right, as long as you get something close to what you want. So, this is helpful, it's especially helpful in that kind of situation where you're like, all right, I know I want to do thing X, and I could write it myself probably, but I wonder if it's already there in the standard library. Especially when you're like not familiar with the standard library, you can find it. All right, that was because, right, fix plus 1 is equal to, by definition, plus 1 applied to fix plus 1, right? Which we could just write it as 1 plus fix plus 1. Right, but that's equal to 1 plus, well, fix plus 1 is equal to 1 plus fix plus 1, right, which is equal to 1 plus 1 plus 1 plus fix plus 1. You see how this is going to go, right? So in this case, it's just going to keep trying to do 1 plus 1 plus 1 forever, and that's never going to actually give us an int. It's just going to be an infinite loop. So to try to start convincing you that this can do something more than just give us an infinite loop, I'm going to do now, so as my type A, I'm going to choose a list of int. Okay, so I need to give it a function, so say fix plus 1 is useless. Well, it's not a loop, right? Just whatever. We use the word loop sometimes in Haskell to mean recursion. So I need to give it a function from list of int to a list of int. Okay, actually, you know what? Before I do that, let's go back to the int arrow int. So plus 1 is one function I could give it, but there's other functions that have that type. One I could give it is the function that ignores its argument and returns 5. Okay, that's a function from int to int, right? So what is this going to do? What do you think? We're going to look at how it's defined and think about what this function does. Yeah.
Would it just return 5 and then ignore the argument?
Yeah. So in fact, it does. Let's think about why, and this is kind of a key point here. So fix lambda underscore 5. You could also say const 5. So there's a standard library function called const that means make a function that ignores its argument and returns this. Right? Same thing. Well, what is that? So that's equals lambda underscore arrow 5 applied to fix. Okay? And now, right, this is the point where the fact that Haskell is lazy, which we haven't talked about a lot, it makes a big difference. In strict languages, right, the way strict languages work, when you apply a function to some arguments, it first completely evaluates the arguments and then passes those values to the function. Right? Like in Java, for example. When you call a function in Java, if you say f of, blah, 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 the first thing it does is it goes and does those, it completely evaluates those arguments. And then it calls f. It doesn't matter whether f ignores the arguments. It just always evaluates them, right? So, and if it did that, right, the first thing it would do would be to try to evaluate this. But of course this is going to turn into this, which would then try to evaluate this, which would, right, and it would just be an infinite loop. Okay? But that's not how Haskell works, right? When you have a function applied to some arguments, it doesn't evaluate the arguments yet. It starts evaluating the function, and if it turns out that it needs the argument, then it starts evaluating the argument. But it doesn't do it until it actually needs to. Right? And in this case, it definitely doesn't need it. So it does not evaluate the argument, it just tries to evaluate the function. And it says, yeah, ignore the argument, return 5. It's like, okay, cool, 5. So that's still not very useful, right? But at least it shows that this can do, it's possible because of laziness for this to do something other than just be an infinite loop, right? And so this is the key, right? The key is if we use some kind of function here that doesn't have to completely know everything about the argument, that either sometimes ignores the argument or might only need to know some partial information about it, then we can get away with this. And it won't just loop. So another example go back to if A is a list of int, I need a function that takes a list of int and returns a list of int. So here's one function I could use. One cons. So I'm using another operator section here, or just like +1 or something. One cons is the function that expects a list and then puts 1 on the front of it. So if I give this, so like if I say, one cons applied to, 3, 5, 6, I get 1, 3, 5, 6, right? So it just adds 1 to the beginning of the list. So if I say fix one cons, well, let's think about what that's going to do. So it's going to result in this function, one cons, applied to fix one cons, which of course is equal to one cons, fix one cons. I don't need parentheses here because cons associates to the right, so. Right, and this is of course going to be, you can see what's happening here, right? It's going to expand into an infinite stream of cons, but again, because Haskell is lazy, it can start printing that out, even though it's never going to end. So if I hit enter, I'm going to have to be prepared to hit Control C quickly. I'm just going to fill up my screen with ones, right? Okay. So that actually produces the infinite list containing all ones, right? I mean, it's conceptually infinite in the sense that it's never going to end, and Haskell can keep producing ones as long as you want. Again, still not super useful, but again, maybe it's like not quite so useless as we thought. Yeah, Gary.
You could call something like take on that if you want
Yeah,
to.
you could. So if you just say like, take 20 of that, well, you get the list of 21. Right? Now, I mean, there's a function called repeat, which does this. So you can just say like, so this is, again, not necessarily like something you would use fix for. Again, it's just a simple example to show that fix doesn't always just give you an infinite loop. I mean, it is an infinite loop, but it's an infinite loop that's like producing ones. The reason is, right, that when we're trying to print out a list, we're like, all right, well, I need to know what the first element is. Oh, the first element is 1, and I don't need to know what this is completely yet. I can start printing a 1, and then ask, okay, what's the next thing? Oh, well, fine. You want another one? Fine. Let's expand this one more and see what it is. Oh, it's a 1. Okay, you can print that out. And it's like, well, what's the next thing? Oh, okay, let's expand that. So it's like, as it's printing, it's doing this expansion while it's printing it. Okay. So, all right, let's write a factorial function, and I'll explain why we're doing this in a second. So factorial of 0 is 1, and factorial of n is n times factorial of n minus 1, right? So factorial of 5 is 120. Cool. I'm going to rewrite, so we've seen this before, I think. I'm going to rewrite the factorial function or something similar to the factorial function in a kind of strange way, right? And then we're going to talk about so we're going to come back to fix, but I'm like, I need to develop this factorial example to see what we're going to do with it. So I'm going to call this fac r. I don't know, fac prime. And we'll come back and write the type signature in a second, actually. So factorial prime is going to take an extra argument. And the extra argument is going to be, instead of calling itself recursively, that extra argument is going to be the function that it should call when it would have otherwise called itself recursively. So it's not going to call itself, it's going to call the function that it's given as an argument. Okay, so we'll call this f. And it equals n times, now I'm not going to say fac prime, I'm going to say f of n minus 1. Okay? Right, and what type does this have? Well, it's given, I mean, ultimately, it's got to take this first argument, and then it's going to take an integer, and then return an integer. And that first argument has to also be something of type integer to integer, right? So it's kind of like replacing, instead of calling itself recursively, it's going to call that. Okay. So let's play with this for a second. So if I say factorial prime, and let's say I don't know what function I'm going to give it. I'm just going to put undefined. Okay, so if it tries to call that function, it's going to crash. However, if I say factorial prime undefined 0, it doesn't need that first argument. It's just going to return 1, right? So that's fine. But if I try with any bigger numbers, it's going to crash, right? Because it's going to call that undefined. It's going to try to call that undefined, right? So if I say 5, okay. So this is like, and I'm going to call this like fact 0. Fact 0 is factorial prime of undefined. So fact 0 is this stupid function that's defined on 0. It's 1. And then for anything else, it crashes. Okay, make sense so far? I'm going to define fact 1. Fact 1 is going to say, let's do fact prime, and the function I'm going to provide to fact prime is fact 0. Okay, so this says, all right, we're going to do fact prime. If it's 0, we're just going to return 1. If it's anything else, we're going to call fact 0 on, like do, n times fact 0 of n minus 1. So let's reload this. So fact 1, of course, on 0 gives me 1. What's it going to do if I give it 1? So we can, if you're not following, we can actually kind of work it out. So fact 1 of 1 is equal to, and this is, I'm doing examples of this because I very much encourage you to do this kind of thing when you're working out issues on homework or whatever, or writing stuff. And I know I've said this to some of you. I don't know if I've said it in class. If I have, I'm going to say it again, right? One of the things about Haskell that's very different than other languages that's a great tool that it gives us is that we can literally reason about Haskell programs just like we can reason about algebra. Like whenever you see an equals in a Haskell program, it literally is telling you the two things on either side of this are equal. I can replace one by the other. Right? I can't do that in, any other language, pretty much. So, well, what is fact 1 of 1? Well, it's defined as fact prime fact 0. Because fact 1 is defined as fact prime fact 0. So it's replaced it by its definition. Well, what is that? Fact prime, well, the argument is not 0, so we're going to use the second case. So that is equal to n, which in this case is 1. 1 times f, which in this case is fact 0, of n minus 1, so 1 minus 1. Okay, so in other words, instead of doing a recursive call, it called fact 0. And this is equal to 1 times, well, fact 0 of 1, of 0, I mean, is 1. So this is just 1. What would happen if so it should say 1. Yeah, what would happen if I say 2?
Wouldn't it be 1 times 1 times 1?
Nope. Silas?
Would it be 2 times
2, so I agree, so if I say fact1 of 2, this is going to be 2 here, 2 times fact0 of 1, 2 minus 1. What is fact0 of 1? What was that? It's undefined, right? It's going to crash. So I just took write that out. So fact1 of 2 is fact prime of fact0, 2, which is 2 times fact0 of 1, which is, I mean, it's 2 times undefined, which just, like, undefined just kills anything, right? It crashes, right? You can probably tell where I'm going to go next. I'm going to find fact 2. Fact 2 is fact prime of fact 1. Okay, so fact 2, right, I'm not going to actually do out the, this thing again, but like, if I call it on 0, of course, fact prime is going to say, sorry, that's just the answer is 1. If I call it on 1, it's going to do, 1 times fact 1 of 0, which is going to be 1. If I call it on 2, it's going to work now, because it's going to say 2 times fact 1 of 1, and fact 1 is defined on 1, right? It'll return 1, so it's going to be 2. But if I call it on anything bigger than 2, it's going to crash. Right, so the point is that think about fact prime, like, because it calls, whatever this function f is, it calls it on an n that's 1 smaller. It's like doing one step of factorial, and then kind of like passing it off to the next function and do the rest. So, as I'm building up, like fact 0 was like a very bad version of factorial that's only defined on 1. But when I call fact prime on that, it adds like one more layer that works. Right, so now it'll work on 1 or 0. Because, 0 is handled just by fact prime, and 1, it like does one level of it and then hands it off to fact 0. And fact 0 is like, yeah, I work for 0, that's cool. Right, fact 2 is going to add one more layer, so now it's defined on 0, 1, or 2. Of course, we could make fact 3 is fact prime of fact 2. Right, and if I do this, so fact 3 is defined on 0. Actually, I can say like, watch, I can say map fact 3, 0 dot dot. So it says it's defined on 0, 1, 2, 3. So on 3 it gives 6. But then after that it crashes. Right? So I'm kind of, you can think of it this way, I'm kind of building up successive approximations to the factorial function. Each time I do this, I'm going to get a function that works like factorial for the first, n things, and then after that it crashes. I don't know if I'll just call it. So here's the question: what's going to happen if I say at n? Well, no. Here's the way to think about this. Right. So fact prime takes this argument, which is supposed to be like the function it's supposed to call to do the next level, right? What if I could pass fact prime itself as that argument? Then basically I would get back the normal factorial function, because that's what factorial does. It calls itself on the next level, right? It's recursive. So I could do that with fact prime if I could, like, if I just pass fact prime itself in that spot, right, then it would call itself. And so the way I could do that, well, do we have a a function that passes a function to itself? We do. It's fix, right? So this is the definition of fix, what we call a mystery here, right? You give it a function f, and it calls that function kind of with itself as an argument. Well, not exactly itself, with, mystery of itself, or fix of itself, which is the version that uses itself, and so on. So you can think of this fix as taking a function that is expecting, okay, no, let's, I'm not going to say it in English part. I claim that this is going to give us something that acts just like the normal factorial function. And let's see why. Well, I'll show you. So fac n of 5 under 20, fac n of 50. And I can call our original fac function, which was just directly written using recursion, gives the same result, right? So why does this work? Let's think about, let's try an example. Like if I say fix fac prime 3. So one thing to remember here is that function application associates to the left. So when I write fix apply to two things, really it means this, right? What is fix of fac prime? Well, it's just fac prime applied to fix of fac prime applied to 3. And I guess now I could take the parentheses off, the same, but now I'm kind of emphasizing fac prime, we're thinking of it as like taking two arguments. The second argument is the number, n, that we want to do the factorial of. The first argument is the function that it should call when it wants to do the next level of factorial. Right? Well, but that function is fix fac prime, and that's the function we started out with. So when it calls this thing, it's basically like calling itself recursively, because that function is going to do exactly the same thing. So this is going to be 3 times, and then it's going to call this function on 2. So fix fac prime 2. Right, which is, well, fix fac prime is fac prime 2, which is going to be 3 times 2 times fix fac prime 1, and so on. Okay. So here's what's going on. This is the crazy thing. So we had this original function factorial that's recursive, right? And then I rewrote it, this fac prime. Fac prime is not recursive, right? It does not call itself. You give it an argument, which is some function, and it calls that, right? And basically, when I applied fix to it, it made it back into the original fac. So fix actually is like the ultimate recursion combinator. So in fact, it turns out that even if Haskell did not let you write recursive functions, so imagine a version of Haskell that a recursion is not allowed. So if you try to define a function like factorial, it's going to say, oh, no, you can't use factorial in its own definition, that's not allowed. Okay, but it did provide fix in the standard library. That would be enough. You could do everything you can do in Haskell today, just using fix. So anytime you wanted to write a recursive function, you could instead write a version like this, that instead of calling itself recursively, takes an extra argument and it calls that, and then you just call fix on that and it makes it recursive.
recursion?
Is there a language without recursion? That's a great question. Um, so, I mean, there's some languages that kind of don't support it very well, but that's a different thing.
It seems kind of fundamental. I guess we've been working with Haskell a lot, but
Right.
when I think of like Python, I guess I can sometimes recursively do stuff in that.
Yeah. I mean, so Python gives you loops, and so you could get away without ever using recursion in Python, and you could just use loops. It turns out that loops and recursion are equivalent in the sense that anything you can do with one, you could rewrite to do with the other. And it would be actually kind of, you could do it mechanically. Like you could make a program to translate between recursive and loop things. So that's one aspect of it. So actually, we're going to see when we learn AGDA in a little bit that AGDA does have recursion, but only kind of limited forms of recursion. So it only lets you do recursion that it can tell is not infinite. And the reason for that is that, as we'll see, basically we're going to be able to use AGDA to like programming the AGDA is also kind of like proving mathematical theorems. Like one thing we can do with it is to write down mathematical theorems as types in the language and then write functions that kind of compute a proof. And if you could do whatever recursion you wanted, then you could prove anything, which would be stupid and not the point. So AGDA actually restricts it so you don't just get whatever recursion you want. So that's kind of a class of language that doesn't have recursion in the sense of not allowing arbitrary recursion. Yeah, but yeah, I mean, but my point is just that like the entire power of recursion, right, could be encapsulated in a single function, right? If you just provide this one function, then you have recursion. And of course, this function has to be defined in some kind of recursive way, right? It could be, but you could imagine having a language where this function is kind of just built in. It's like specially built into the implementation. And then beyond that, the language itself doesn't allow you to define recursive things, but you could still use it that way. So this, partly it's kind of a curiosity. Partly it does actually have some practical implications. For example, there's some cool things you can do. I'm not going to go into this, but if you define functions in this style, you can kind of like, how do I say this? You can like compose them with other functions that sort of add extra behavior before you call fix. So if you're like, oh, I want to have this function just like Factorial, except I want it to like print out the argument that it got at each step while it's doing the recursion. Or I want it to actually like remember, like have a table of results so that when you call it again with the same input, it will just look up in the table, right? You can kind of like add those behaviors by composing other functions and then call fix at the end, and you get a function that that does that. Whereas if you just write Factorial like this, it's kind of just like this closed box. You can't reach inside and be like, oh, I want to add this behavior in the middle of the recursion. But you can do that this time. The other thing this gives us is that if we can basically encode something like this function, like fix, in the lambda calculus, and that shows us that we can do recursion in lambda calculus. And it turns out that we can. So yeah, let me show you that really quick. Okay, so the first thing I want to show you is function by itself says, we're going to take an argument x, and then we're going to produce x and x, x applied to itself. So if I call this on like, f, I'm just going to get ff, right? Whatever I apply it to, y, z, y, z. I could do like, if I do this, I'm going to get lambda z dot z applied to itself, lambda z dot z. And lambda z dot z just returns whatever it's given. So that thing would then reduce to just lambda z dot z. Right? So I duplicate this thing, applied to itself. And then, well, this one is applied to this one, it just gives this one back. Okay. But here's the thing, what if I apply this to itself? Or copies itself, right? Well, this function takes its argument and just duplicates it twice and just applies that argument to itself. So, if the argument is lambda x dot xx, I'm going to get this thing duplicated and applied to itself, which is exactly what I started with. Right? So, right, every line is the same because reducing this one step just produces exactly the same thing that we had before. And fortunately, the lambda calculus thing, it stops after a certain number of steps by default. But I mean, it would keep going, obviously, if we let it. Okay, so this is kind of useless, but it shows a couple things. Number one, it shows that you might wonder whether any lambda calculus expression, if you reduce it enough steps, will eventually stop and give you like a thing that doesn't reduce anymore. So, turns out that's false. Right? It's possible to come up with lambda calculus things that never stop reducing. And this actually was kind of a big problem. So when Alonzo Church came up with this system, he kind of was intending for it to be like an alternative foundation for mathematics. And it turns out, in a precise sense that we'll talk more about later, this kind of killed that idea. Because, again, it kind of meant that, well, yeah, we'll get into that more later. But I don't just want something that reduces to itself. Ultimately, I want something like, I want a thing, which we're going to call y, such that if I apply it to f, it's going to reduce to f applied to yf. Right? This is what the fixed function does in Haskell. So we're going to call it y because in Len calculus it's typical to call it the y combinator. Right? I want it to, if I apply it to the function f, I get f applied to yf, which would give me f of yf. And if you just keep doing f. And we've seen that that's what fixed does in Haskell, and that gives us the ability to write recursively. So can I come up with a way to do this? Well, what if I do something like lambda f dot lambda x dot f xx? So here I get like an extra f. Is this the way to do it? I need this in other order. Yeah, that's the way to do it. So here it looks the same, except I'm taking this extra f argument here. And instead of just saying xx, I'm saying f applied to xx. So this first one, right, if I apply it to two arguments, so let's say, call it capital F, just to distinguish from lowercase f. So the first argument to this thing is going to be, the x. And that's going to be this thing here. So that's going to go in here for this x. The second argument to this is going to be capital F. Capital F is going to go in here for little f. end up with capital F applied to this thing applied to itself. But this thing applied to itself is exactly this whole thing that I started with. This is not quite right. Because if I do this, yeah, no, okay. What am I missing? That's interesting. That doesn't look like the same as what I've seen before. Maybe that's the right way to do it, or maybe that's just a slight variant. Anyway, whatever. You can see that this works, right? So we ended up with, like, as the more times we reduce it, we get more and more just applications of F to itself, right? So if I define y equals that, right, then like y applied to F is gonna give that. Can we do a simple example? So let's say this simple example 0 is lambda successor takes an n and then gives us a number which is lambda s and s of n s. Alright, we did this the other day. I'm not going to go over this again, but we need plus. You're supposed to do this on your homework, but so I'm not going to talk about it. Okay, so now, let's make the function that just like, when I give it n, it does like n plus n minus 1 plus n minus 2. Oh no, wait. We need subtraction for that. That's annoying. Subtraction is very hard. I think it's like a level 2 exercise in homework. Let's imagine that I had it. So here's what I could say. I could say, sum prime equals lambda r. So this r is it's going to take, lambda r is the thing it's going to call instead of calling itself recursively. And it's going to take a number n and say like, I guess this is, okay. Never mind. I want to say something like this. Lambda r, not lambda n. I'm going to say like, if n is 0, then return 0. Else, return, r applied to the predecessor of n, like n minus 1. We haven't defined pred and we haven't defined if 0. I think both of those are on your module, but so it doesn't like that. But like I could define that, and if I did that, then I could just say sum is y of sum prime, right? So it takes that non-recursive definition, it takes this extra argument that it calls instead of itself, and then if I just apply y to that, it kind of passes it to itself as it unfolds so that it actually makes it into a recursive function. So this is how we can encode kind of arbitrary recursive functions in the lambda calculator. And that's kind of like the last missing piece that we need to be able to do whatever computation we want. Once we have recursion, then we can pretty much do